Afternoon for this today's Earth Talk on critical minerals. My name is Rudy Slingerland. I'm a professor of geology emeritus in geosciences, and it's my pleasure to introduce today's speaker, Dr. Jesse Remick, who's an associate professor of geology of geosciences, I guess, in the Department of Geosciences. Jesse got his undergraduate degree at Hope College in Holland, Michigan, and a PhD from the University of Alberta, and then was sufficiently accomplished, apparently, to get a postdoctoral fellow at the Carnegie Institution, Department of what was then Terrestrial Magnetism, which is curious, but studying the early evolution of Earth's crust and continents. Hired at Penn State in 2019 in time for COVID, and now is an associate professor with interests in ore deposits over a range of geological situations. And this, for those of us who are old like me, is a bit of a resurrection for geosciences at Penn State. Of course, only I have the time to count the number of theses and dissertations in high temperature pressure experimental silicate and oxide systems and ore deposits. And from 1950 to roughly 1990, there were 125. And after that, none. Because, of course, interests change. And so I find it curious that we come back around trying to solve global warming and climate problems by looking for ore deposits again, although particularly peculiar ones. And so Jesse's going to talk today about concentrating mechanisms for rare earths in pegmatites.
All right. Thanks, Rudy. Okay. Thanks, everybody. This is, as with all talks that have an overly long and overly complicated title, there's not going to be many conclusions, I think, in here. This is certainly, as I think you said, a rebirth of the field of economic geology. For me, or a rejuvenation maybe. For me, it's sort of a rebirth because I'm not an economic geologist by training. I studied really old rocks in northern Canada for a long time. And, it's focusing on getting maybe more societally relevant and getting into sort of casting a wide net, exploring the problems in this world of critical metals. So this is the work that a whole bunch of students in my group have done. Renan Beckman, Eric Schoonover with PhD students who've taken the lead at various times in some of the projects here. And really the bulk of the work's been done by 3 undergrads, Niles, Andrew, and Mike. Niles graduated last year. Andrew and Mike are doing their undergrad theses right now. And then Maureen and Feynman helped a lot with analytical work, and Dwight contributed samples here. I'm going to focus on pegmatites. So some introduction on pegmatites, pegmatite geology. I'm going to focus really on 2 data sets that we have from 2 different types of pegmatites that are very exploratory, and I'd say we might have a testable hypothesis idea at the end of it, but nothing more conclusive than that. Here's an Archean pegmatite. This is a 2.7 billion year old sediment that's been metamorphosed at high grade at 2.58 billion years by a granite that's just off to the right of this, and this is a pegmatite sample. And so this is one of the earliest pegmatites that we know of on Earth, 2.6 billion years ago, with very coarse-grained mineralogy in it. I really don't like pointing with this, but we'll make do. So we're going to look at these and look at the geochronology of them. And I'm going to kind of show off some of the analytical facilities that we have here at Penn State and go through some workflow stuff. So a big introduction to pegmatites, introduction to the methods we're using, geochronology, and then kind of 2 case studies in different pegmatite systems in really complicated minerals that I don't fully understand yet. So, okay. Introduction to our basic first order workflow. This was an image that I think Renan made initially in our group and then has been repurposed and revised over time. But this is the workflow. We're looking at zircon minerals. The top right here, top left, is a mineral grain in a mount. So that green ring is kind of represents an epoxy mount. We have a laser ablation system at Penn State. We've called it the Lioncron Laboratory in the Geosciences Department. Here's our laser system in the middle. We have a mass spectrometer here that measures the uranium lead isotopic ratio of minerals that are blasted by the laser. And then this instrument over here measures the trace element concentrations in those mineral phases. So we'll blast a hole in the grain, drilling down in, sort of orthogonal to the growth zoning, ideally. As we drill into the growth layers, then Renan and Mike and Eric have spent a lot of time doing the very tedious exercise of plucking these little sand-sized grains out of the mount, rotating them 90 degrees, remounting them, and then polishing down in so that you can see the depth profile, the laser hole that we drilled in. Then we get an image like this. This is a secondary electron microscope image showing from this instrument over here in the Materials Characterization Laboratory that was just purchased this year. So this is that little depth profile that we're showing. So the laser hole blasted in there. We can image this. We can characterize the major element concentrations. This is a trace element map, or a major element map of a zircon grain, of that zircon grain actually done at the microprobe here. So we go over and make a map of the chemistry of that grain. And then we can go back to the laser here and put more holes, little pinpricks with the laser into that system and date the ages in the age zonation here. So then we go back to the laser. So start the laser, come back to the laser. And that's kind of the workflow that I'm gonna show for a couple samples. Okay, a little bit about pegmatites. This isn't it. I have some textbook examples of pegmatites. Some of them are a little grainy because they're old photos, but pegmatites are really coarse-grained, igneous-ish rocks, let's say. They have this crazy zonation in them. They've long been the domain of mineral collectors and, people who love weird phases of beryl or weird minerals that, have found one place on Earth. They've long been focus of interest for those groups of communities, less interest for the sort of general geological concepts here. Because they're very small, they have enrichments in metals and minerals that are rare by definition in some ways. We often have this zoning. So this is an example of a pegmatite. Here's the background rock, the country rock here. There's a zonation to the minerals here with some border zones, some core zone, and this would be kind of where all the goodies are enriched. And a couple more examples of this. They're famous for having ridiculous mineral sizes to them. Some of these grow very, very rapidly by some people's claims. But regardless, huge minerals, huge grain sizes, probably growing from a fluid, almost certainly growing from some kind of fluid, not a silicate melt, not magmatic per se, but perhaps related to magmas. And then here we have a lithium ore. So lepidolite, the pink stuff in here, and then this is spodumene, a lithium ore mineral. So this would be a lithium ore pegmatite rock, and we can see here's 5 centimeters. This is a fairly coarse-grained rock by anybody's designation. So this is kind of what we're focusing on. This is the value of pegmatites. I don't like showing tables, and I don't recommend that people do, but this was just a really nice summary from the Green Peg program that was, some publications came out recently that kind of did a review of pegmatite exploration techniques, pegmatite scientific understanding, and I'll highlight the important parts here. There's 2 categories, lithium, cesium, tantalum, or LCT pegmatites on the left there, and then NYF, or niobium, yttrium, fluorine pegmatites on the right. Some of the minerals of interest, spodumene, pedalite, columbite, tantalite, those are lithium and tantalum niobium ore minerals. Also pollucite here is a cesium ore. And then notice rare earth elements occur in things like alunite, monazite, zircon is another one in these NYF groupings of pegmatites. So 2 different kind of chemical categories of pegmatites. I'm going to talk about one case study from an LCT pegmatite up in Maine, and then one that doesn't really fit with the NYF pegmatite class, but has some similarities to that in our second case study. Okay, so pegmatites have a well-studied and well-characterized, I would say, maybe not well understood, but well-characterized morphology to them. As I pointed out before, we often have this gabbro would be the country rock here. This is an example from California. The country rock, we have an altered rind along the country rock on both sides, and then we have these near country rock zones, intermediate zones, and then core zones. So they're kind of internally zoned as we go from the core of the pegmatite to the rim of the pegmatite, and generally thought to be that the rarer the element, the more concentrated it'll be in the core zone, typically. And then we also have these murialytic cavities, which here's kind of a schematic outline of what one of those might look like. And these would be where the gem minerals are formed. These are actually cavities in some instances. Sometimes they're completely crystallized, but this would be growing from a very volatile, rich fluid phase near the last stages of the crystallization of this pegmatite. So pegmatite body perhaps intrudes in the kind of textbook model, intrudes in and crystallizes from the edge to the center, sometimes thought to be very, very rapidly crystallizing. And so we get enriched, the dregs in the middle here get enriched in all the goodies that don't want to fit into the major minerals in the edges there. So we distill this thing, internally distill this pegmatite, and end up with murreolitic cavities. We'll come back to those murreolitic cavities, I think, at the end, maybe. Okay, so the enrichment process, that says pegmatite enrichment processes here. People have looked at this for a long time, and I think the geological maps are sometimes some of the interesting ways to look at this. This is from the Harney Peak granite in the south, the Black Hills of South Dakota, famous pegmatite locality. Here's the Harney Peak granite down here in the dark gray. This is a Metigrewacky, a sediment country rock around it. And then these are maps of lithium concentration in the sediment as we go around there. So some famous pegmatites that get fairly concentrated in lithium, and we have these kind of hot spots around it. But maps like this kind of led to the idea, well, if we look at the traceomic chemistry of the rocks as we go away from this granite deposit, or the granite itself, we get a decrease. So this is lithium over magnesium ratio in pegmatite halos, quartz veins, and the regional background Grewacky is down here. So as we go away from the fluid source, in this case, the granite, there we go, recording now, okay, good. So back to the beginning, pegmatites, no. This is, the Grewacky samples are the background here, and basically the idea here is that the pegmatites in the veins, as we move away from the fluid source, which is the granite here, we decrease lithium over magnesium ratio. And show this is fluorine aluminum ratio as well, that as we get it further away, we get decrease of lithium, decrease in fluorine, which would lend to believe that the magma is the source ultimately of many of those things of interest, like lithium and fluorine. Is that the case? So things like that, examples like that, have led to kind of a theoretical model for pegmatite formation, that they're either related to the plutons themselves, or they're related to melting of the host sedimentary rock, but it's melting or melt, one of those two. But we get a melting zone or a melt zone, which would in this case be represented by the pluton. As we move away from that pluton, the early pegmatites, basically this huge batch of magma crystallizes. As it crystallizes, all the elements and fluids that don't fit into the major constituent minerals get enriched in what's left behind in the magma chamber. And that ends up being a fluid, a high temperature fluid that gets exsolved out from the magma chamber and intruded into the country rock around it, flushed into the rock around it. The first pegmatites would be, in this model, barren, because they're enriched in all the goodies, but not that enriched yet. And those pegmatites need to crystallize, and then the later stage pegmatites actually get more enrichment. There's a double enrichment step going on here. So barren, then we get pegmatites enriched in rare earth elements and beryllium, then beryllium, niobium, tantalum come on the scene, then lithium, cesium, tantalum way out at the edge. That doesn't necessarily hold true. This is, again, from a review from this Green Peg program. I'm not going to try and pronounce the name of this pluton here, but this theoretical source pluton, and these are lithium concentrations in quartz in a bunch of veins and pegmatites away from there. And there might be a general trend towards increasing lithium, but you have very high lithium quartz nearby and very low concentration quartz, very low lithium concentration quartz further away. So not necessarily mapping perfectly onto this traditional model. Similar thing goes for another situation where we have a shear zone, and we have barren and spodumene bearing, that's the lithium ore bearing pegmatites right next to each other, all intermingled into this shear zone. So not necessarily, again, in agreement with the theoretical model. It's also worth pointing out that in the last decade or more, probably a little bit more than that, igneous petrology has had to sort of deal with some of the facts that granites are actually metamorphic rocks at their heart and soul. So this is a picture of the Yosemite National Park, which is the Tuolumne Intrusive Suite, a huge, huge batch of granitic magma, broadly granitic magma, zone plutonic complex, sort of the template for studying granites, one of the templates for studying granites around the world. This is a large package of granite that has intruded over 10 million years. And the rocks look something like this. And many of the mineral phases in these rocks, although we traditionally pick these up and say, oh, look at this. This looks like a granite. This is crystallized from a magma. Great. However, these things have sat at very high temperature, crystallized at 680 degrees centigrade maybe, but they were at that temperature in the solid phase for many, many millions of years. And so, as was pointed out in 2018 in and other work since then and before that. This is a map of a titanium quartz crystal. So this is all this is all quartz. The high magmatic temperature quartz is just the core. And if we do a volume estimate about this, it's actually a very low volume of the quartz in this rock that records magmatic temperatures. Most of the rest of the quartz is actually low temperature, below magmatic temperature. So even in these big granite provinces, there are fluids, this is a metamorphic rock ultimately. So metamorphic-like processes are happening in these systems. And fluid is probably a major player in those. So why would the same not be true for pegmatites? And in fact, we have these muralitic cavities. Okay, so fluids are working through these processes, through these systems a lot. They are very complicated, weird minerals that are not common, therefore hard to date. And so we're going to focus on the geochronology of these pegmatite systems. And really, how many enrichment steps are required to create an ore body? That's kind of one of the classic questions in economic geology. So do you just need one enrichment step, or do you need multiple factors that all coalesce in one part to make a really useful ore deposit? We are going to use zircon. Zircon is a great mineral. My wife once asked me what my favorite mineral is, and I had to say, well, what do you mean, for science or for fun? And she looked at me like I was crazy, because what a stupid question. Why do I need that qualifier? But zircon is my favorite mineral for science. Because it's not necessarily the most beautiful mineral, although this is a very pretty zircon mineral, but it rarely occurs in this phase. It's zirconium, silicon, oxygen. It is found in a wide variety of rocks, and it's very resistant to, although not immune to chemical overprinting. So here's an example of mineral grains. We can find these in beach sand. We can find these in the quartzites up on the ridges around here. We can find these in granitic rocks. And we separate these in the lab, separate out all the zircon grains. They look like a big pile like this. We mount them in an epoxy mount, and then we polish down in and look at the grains with something like an SEM. So this is it's actually a 4 billion-year-old zircon grain from my PhD work with a cathodoluminescence image of the nice zonation here. So we can see this oscillatory zoned growth rims. This is indicative of growth from a magma. We have a metamorphic rim around here that has a very different age to it. And then some complexity, some cracking and things like that are going on. That this is an old and tortured zircon grain. And we're going to look at some even more tortured grains from pegmatites. So this is what a relatively nice zircon looks like when we polish down in and image it. It's a great geochronometer. It takes in uranium when it grows, but it rejects lead. And uranium decays to lead over time. And so this happens at a fixed rate. This is radioactive decay. We love this in the zircon world. So we can take, because uranium decays to lead, we can take the lead-uranium ratio. So it's basically a sand dial. If we have uranium up here and it's slowly dripping through our sand dial at a fixed rate, we can just measure the amount of uranium up top, the amount of lead on the bottom. There's a ratio there. And if we understand the decay constant, which we do very well, then we get time out of that equation. We don't just measure uranium though. We have a couple different flavors of uranium. As we know, when we think about uranium in society, natural uranium here is 99.2% uranium-238. And there's a little tiny fraction of uranium-235. When you think about reactor grade enriched uranium, that has a little bit more U-235 artificially enriched. And then weapons grade is very heavily enriched in 235. So 235 is the isotope of, let's say, interest for nuclear power and nuclear weapons, but it's not very common in natural uranium on Earth. But back in time, it was, and that's really important. So if we look at the relative decay, uranium-235 decays faster than uranium-238. If I just said, okay, we had 100 atoms or 100 grams of uranium-238 4 billion years ago when the Earth formed, so here's 4.5 billion years ago. If I had 100 grams of that today, half of that's decayed away. We've undergone basically one half-life in uranium-238. 235, we've undergone almost all the half-lives, 6 or 7 half-lives, so almost all of it's decayed away. We only have a small percentage of the original 235. And that's really the power of the uranium-lead decay system. And the power of zircon is that it preferentially incorporates uranium but not lead. So it gives us a relatively pure look at our geochronometers. So we can do the sand dial exercise, and we have 2 different sand dials where the top of the sand dial is filled with uranium of 2 different flavors, and the bottom accumulates 2 different flavors of lead. And we get 2 different ratios with 2 different independent age estimates from it. And then we can compare those and contrast those ages to one another. And that's what we do. and I'm banging on about geochronology here. I'll get to the point here. You'll see this, you'll see plots like this. This is why I'm explaining it in some detail. And it gets a little complicated when we're down at the young age end of the age spectrum. But this is our Weatherhill Concordia plot. Zircon uranium-led geochronology is a huge, vast literature. It's one of the earliest geochronometers used in the 50s for geochronology. And this plot was derived actually at the Carnegie Institute of Washington, D.C. It's called the Weatherhill plot. But on the y-axis, we have one of our geochronometers. We plot 206 lead over 238 uranium. That ratio gives us an age. 207 lead over 235, that's the other system. That gives us an age. So two different ratios, two different ages on the axes. And where those ratios give the exact same age, we plot a line in space that's called the Concordia line. And so that's where the ages agree. If we make a measurement with our laser ablation system, we get a data point, we get an average with some uncertainty. That uncertainty becomes an ellipse in our plotting system. So this is the uncertainty of our data point. And if that data point overlaps the curve, the Concordia curve with an uncertainty, it means the two ages agree, and that might be a reliable age. So 1.5 billion years ago, that might be a reliable age for this hypothetical zircon analysis. It's almost, well, it's not almost always the case it's almost never the case that they're perfectly concordant. It's very rare that they're perfect like this. And in fact, we often have in the grains we're going to see, these are really altered grains. They're in pegmatites. They're really damaged. And so they rarely plot on this line. Instead, we have a scenario like this where we might have a resetting line. And the resetting is a linear phenomenon in zircon space. So if we have a 1.5 billion year old granite that formed and crystallized zircon, and then that zircon sat there for a billion years and underwent some metamorphic resetting event or fluid alteration event 500 million years ago, those zircon grains would get perturbed, and they'd get perturbed perhaps, hopefully, at variable amounts, at variable degrees, where the more perturbed ones plot further down towards 500 million years ago. And then that metamorphic event or that alteration event happened, and then 500 million years progressed between then and now, and these data points evolved in that space, but they still plot along this linear array. And so even if we have a data set that is not concordant, doesn't plot on the line, but they plot along a linear array, we can regress a line through that, calculate some uncertainties, and look at the upper intercept and the lower intercept, and those in our interpretations have age meaning, potentially have age meaning. So that's the exercise we're going to look at with both of our data sets, actually. Discordant data that may or may not have age meaning in the upper and lower intercepts here. Okay, enough about geochronology. Let's move into some of our examples. So the two we're going to focus on are the mountain mica, lithium, cesium, tantalum pegmatite up in Maine. It's up in there, right in that area. And then the Nechalacho, formerly Thor Lake, rare earth element, niobium, tantalum, zirconium deposit in the Northwest Territories of Canada, my home turf up there, up in that region. Okay, Mount Mica pegmatite, a little introduction about it. Here's a map from Dwight Bradley, who compiled lithium, cesium, tantalum pegmatites and geochronology a few years back. There's a map of the Appalachians here. The southern Appalachians have a pegmatite district. And, the North Carolina pegmatites here, down in Alabama even. We've got some pegmatites. Unfortunately for us, we live in the Central Appalachian LCT gap. So it takes us a while to drive to a pegmatite from here. But when we get up into New England, we also have a huge amount of lithium pegmatites up in here. Mount Mica is right there. If we look at this geological map, again from Dwight Bradley's work, the white areas here are all granitoid rocks, so plutonic rocks. There's like 250 million years of magmatism in this region. So a huge age range, age spectrum of magmatism. The purples are all sedimentary rocks that are metamorphosed at various grades. And there's Mount Mica right there. So that's the one we have samples from that we're going to look at. Here's a map, or here's an image of the mine. You can see background metasediment on top, the pegmatite, the area where people have mined and are continuing to mine in here. Mostly gem collectors and things like that. And you can see it's a weird termination right there where the pegmatite stops and continues. So these are really complicated geological phenomenon. They're small, discontinuous, and therefore a little bit hard to map and understand. Here's a different New England pegmatite that has, I show this because there's muriatic cavities, that some of these are actual cavities and some of these are places where miners have worked them out, have kind of dug out in there. But you can kind of see the zonation a little bit better. We have a bunch of schorl in here, a line of schorl, and then the kind of a sort of a purplish hue down here, which I'm not sure, but I think it might be lepidolite rich area down here. So lithium rich zone perhaps in these muriatic cavities, just to kind of give you a sense of the zonation here. An image into one of these muriatic cavities with quartz veins, or quartz crystals, big quartz crystals clearly growing into space, so growing into a fluid. And then another muralitic cavity here with nice, beautiful gem crystals growing into them. So very pretty, very cool rocks, very interesting to mineralogists, and very complicated rocks for geochronologists. Here's back to the Mount Mica deposit. This is from a great master's thesis that talks about this garnet line. So there's this line of garnets here. And above this line, we have lepidolite and spodumene, two lithium ore minerals. So very lithium-rich pegmatite up here, clevelandite line, and then a garnet line interspersed in there. We'll come back to that garnet line and perhaps how that relates to our data. The geochronology, complicated geochronology from pegmatites. This is a compilation Dwight put together in 2016, updated in, I'm not sure if it's quite published, in 2025. But the point here is that the number, the N over here, is 66 pegmatites globally with dates from lithium, cesium, tantalum. And there's some age peaks. Some of the older ones, that one I showed in northern Canada is part of a huge pegmatite field of lithium pegmatites 2.6 billion years ago. These broadly correlate to supercontinent formation events, peaks in crustal growth or crustal maturation that we think occurred during this interval. But the point of showing this is that there's very few, the N is very small. We don't have many pegmatites that we have good dates on, and people are working on this, but I'm going to show why that is. Here's a map, well, kind of a map. This is an age map going kind of from north to south through that chart that from Dwight Bradley earlier that showed all the pegmatites up along the Appalachians. The point here is that the top is 220 million years ago. The bottom is 400 million years ago. And we're going to work on, this is Mount Mica here in Maine, and work through some of the geochronology. So the blue, go back. The blue hexagons here are muscovite argon geochronology. So those are basically minimum ages. The pegmatite itself has to be older than that, so the interpretation goes. So you can see here, this is 254, 260. Down here we have xenocrystic zircons, so these laser ablation data, and the xenocrystic ones, the gray boxes, or the brown boxes. Those are xenocrysts, so zircons from the country rock that are found now in the pegmatite have been aggregated by the pegmatite itself, so therefore they have to be older than the pegmatite. So in the case of Mount Mica, we have 250 to about 370, about 100 million year age bracket. And there's an apatite laser ablation ICP-MS age in there of 268 in that case there. So this is kind of what we're working with. It's pretty tough. There's minimum and maximum minimum ages with a big age range in between. And then there's not a ton of geochronometers in the middle here that are necessarily reliable. Cassiterite is one that people have used a lot. This is a tin oxide. And so this is a growing analytical tool. It's dating a tin mineral, actually. So lithium, cesium, tantalum often correlates with tungsten tin deposits in many terrains. And so this gives an age. It's a different uranium lead plot, but 256 million years is the regression here. So 256, 260, those are the apatite and the cassiterite are giving similar ages. So the pegmatite formation broadly might be 250. Okay, what did we do? Well, Renan took the first crack at some of this data during her PhD. Eric's been helping throughout the whole process, but then really Mike has taken this on board as his bachelor's project, starting early in the summer and then continuing on through his thesis this year. We got some samples from Dwight from Mount Mica, some zircons that they'd separated, those really complicated ones where, I forgot to mention it, but here are the zircon data. Each of these are thermal ionization mass spectrometry data, so they're really precise, but there's no spatial resolution to the data. So dissolve a whole zircon grain. We got a bunch of discordant data points, so each of these are really hard to interpret, impossible to interpret on their own, and there's no real linear feature to this data. So we can't put a single regression line through it and do that upper intercept, lower intercept game with it. What we do, there is a concordant data point down here, which ends up being this xenocryst. So this gives us the sort of maximum age of the pegmatite, but it's messy. That's my main point there. This is very messy. Okay, so we looked at this zircon grain. We are using here, we've skipped ahead to this stage here where the grain, this was depth profiled. The depth profile is off the screen here. Plucked, rotated, mounted, polished through, and now imaged with the secondary electron microscope, the scanning electron microscope, excuse me. And then I'll show some microprobe maps. But we have this core rim relationship. So the core is really, I think you could see, senses that it's really damaged. It's cracked. There's all these sort of holes in it. This is a term called vacuolized. This thing has been heavily, heavily altered. Very little of this is pristine zircon anymore. Whereas the rim looks like, it's kind of decent mineral growth zones, okay? Here is our microprobe, major element chemistry. This is a uranium concentration map. Uranium usually occurs in zircon, but not at weight percent levels. It occurs in the hundreds of ppm levels. So this is a crazy amount of uranium for zircon to have high fractions to weight percent of zircon in this rim. There's hot spots of uranium in here that are probably uraninite in the core. But if you look at that spot right there, probably this spot right here, it's pretty low uranium in there, though measurable and important. It also has fluorine in it. And fluorine, this is not, I wouldn't believe any one pixel's data here because it's pretty low concentration, but it is on average higher in the core, and we don't really find much fluorine in the rim. So interesting. This is a phenomenon documented in hydrothermal zircon from pegmatite deposits like this in a few locations, but very few people, nobody that I could find has been able to date these rims like we're going to attempt to do in the next couple slides. So fluorine-rich zones are not, they're really weird zircon compositions. They've been documented from a few locations though. It's not entirely clear how they're forming. And then calcium, again, calcium is a 2+ ion, so this should not go into the crystal structure. We usually use calcium as an alteration metric. So if we see calcium in a zircon analysis, we usually discard it and say, oh, that's been altered. We don't trust that data. This does not look like that. This looks, I mean, I can't say it's structural, but there is sort of zoning patterns. It looks like there might be oscillatory zoning in some way in the calcium concentrations here. And again, weight percent calcium in this thing. So a really, really weird zircon crystal structure here. Some very interesting substitution mechanisms going on. So what did we do? Well, we took it to the laser, took it back to the laser. And Mike put these spots on here, 2 in the core, 4 on the rim, and then numbered 1, 2, 3, 4, 5, 6. A couple other grains where we have, again, these rim-core relationships. And here are some spots on a really altered, damaged grain. And just looking at these are atrocious looking zircons. These are really terrible. I would not expect to get anything of age meaning out of this. But we're interested in crappy looking zircon these days. So let's take a look with the laser and see what we can get. Here are those data. So these are the uncertainties around the mean and uncertainties of each of these data points. So this is the number 1, number 2, number 1, number 2, the 2 core analyses from this grain, the core analysis from that grain, and all 5 rim analyses plot down here. So something of a consistent story. The rims are further down, the cores are up high. That's good. I mean, the cores should be older than the rims, but none of them plot on Concordia at all. And the age of the pegmatite, remember, is like 250, 260. So we have some stuff that's looking older than that and a lot that's looking younger, but nothing's on Concordia. The important thing to remember is that this is a curve in space. So even though this looks linear in this plot right here, it is a curve in space, even at this young end. And so we can do this linear regression thing. So the traditional techniques would just say, put a linear regression through this data where the lower intercept hits the Concordia line. We can calculate the age of that plus some uncertainty. Same thing for the upper end plus some uncertainty. And this is what we get. We get a lower intercept of 73 plus or minus 18, an upper intercept of 430 plus or minus 45 with some large uncertainties on that. Okay, so what the heck? The upper intercept kind of makes sense. Similar if I go back to Dwight's, this stuff here, okay, a xenocrystic zircon of 450, somewhere up in there, would make some sense. This is intruding into sediments that have detrital zircons of that age. That kind of makes some sense, fine. The data are linear and broadly correspond to the texture. That's pretty good. But what about this lower intercept? What is that age, and does it record anything of interest? Mike gave a poster at GSA and I think maybe took a little bit of criticism for this age perhaps and whether it has any age meaning or not. And the reason for that is there's no geological events in the zircon record or most geochronology record from New England that says there's any event of any note that's happening at 75 MA in this region. So back to this map from Dwight Bradley, the white areas are again the igneous rocks, the plutonic rocks. This top plot is a compilation of the ages of those igneous rocks from 600 million years down to 0. And you can see peaks at 125, 200, et cetera, all of our orogenies in this region, and big peaks in the 400s, but nothing younger than 100, nothing near 75, nothing of note at least. So what's going on with this? What do we think? All right, well, back to this master's thesis in this garnet line. So lithium-rich stuff up here, a garnet line, and the garnet line is not an uncommon phenomenon in pegmatites. But this thesis looked in detail at some of the textures in Mount Mica and noticed, as others have, that these garnets are altered, and they often have these tourmaline rims. So this garnet has a tourmaline rim growing around it here, a couple different phases of tourmaline. This garnet from the same suite of outcrops has a muscovite pyrite rim growing around it, and then some SEM images showing again alteration of the garnet, where there's actually this pollucite, this cesium ore mineral with muscovite growing again at the expense at the reaction rims around the garnet growing with some enriched fluid, some fluid enriched in some of our ore metals here. So the conclusions from this were that the miners historically have noted that pockets and lithium mineralization often equals garnets having tourmaline rims. So these murulatic cavities are associated with the lithium mineralization, and when that happens, the garnets have tourmaline rims. And they associated these things with perhaps the cavities releasing some sort of late-stage metasomatic fluid. And the question here is late stage. What does that mean? Enriched in cesium, fluorine, rubidium, water, etc., that are going in and doing all this alteration to these phases. So I'm not sure at all if this is a reasonable hypothesis, but perhaps that's what we're seeing here, is rupturing of the murulatic cavities or expulsion of these fluids, or maybe external fluids that are calcium, fluorine rich, that are actually inducing crystallization of the zircon, of these zircon rims at something like 75 million years. I'm sort of cautiously convinced that this regression has some age meaning. The upper intercept makes sense. There's textural relationships that make sense along the line itself. It's a linear data set from 3 different zircon grains. I think it might have age meaning, but what it is an open question. And there's some clear hypotheses to test here. Probably would require going back and investigating the pegmatite in more detail. But maybe it's a cavity rupture, local resetting around 75 million years with this really reactive fluid flow, and that would speak to multi-stage hydrothermal enrichment processes, whether that's a fluid internal to the pegmatite, like a murulatic cavity, or some other fluid coming in from externally sourced and doing this resetting and enrichment process. But it speaks to the complexity of these grains in this phenomenon. Okay, so that's part 1. That's the LCT pegmatite story. We're going to move on to the Nechalacho, the Thor Lake deposit up in the Northwest Territories of Canada, up in here. So we're going to show a couple maps from up there. This is a rare earth element, niobium, tantalum, zirconium deposit. Not really it doesn't fit perfectly in that NYF class of pegmatites, but it's a very complicated suite of rocks with a potential, well, with a pretty large rare earth element deposit associated with it. So we are up here in the Northwest Territories of Canada. This is Great Slave Lake here. Great Slave Lake. We're zooming in right here. Yellowknife is there, kind of the end of the road. Ice Road Truckers country there. To the north on this map, the whole section up here is a huge tract of craton, really old, really thick, stable craton. The first image I showed on the title slide of the lithium pegmatites are actually from just in here in their 2.6 billion year old pegmatite district. Here we're on the margins and we're associated with this huge shear zone. And so on the margins of cratons is a good spot for mineralization, in part because on the margins is where we probably can get fluids into the crust and have multiple pulses of reworking events over geologic time. This place is no different. The Thor Lake deposit's right, or the Nechalacho deposit's right in the middle. The Grace Lake granite surrounds it. Thor Lake syenite there as well. And then we have this Nechalacho layered suite in the middle. If we zoom in on that, we've got the Grace Lake granite, the Thor Lake syenite, and then this mineralized zone. If we focus in on the T-zone, what they call the T-zone here, a geological map of the T-zone, we have a quartz core with different enrichment zones in this thing, all cut by a diabase dike, a younger diabase dike there. Really complicated mineralogy again. Lots of rare earth element carbonates, zirconium moving around. So we've got bastnasite and parasite and synchosite and eudialyte and all sorts of crazy minerals that are pseudomorphing each other. Here's an image of a pseudomorph from an original grain that has been replaced by very small fragments of zircon and bastnasite, etc. Very complicated mineralogy. Here's some pseudomorphing going on. This is the original grain boundary that's been replaced by quartz, calcite, monazite, zircon, allanite. So that's a fairly strange allocation of minerals there. These are weird agglomerates of quartz and zircon intergrowth textures. Again, altered zircons over here. So these are very non-traditional zircon deposits. And this one, I just had to show this slide. This is a very interesting example. We have zircon growing here, and then also zircon growing here. So this looks all the world like a Mississippi Valley sphalerite growth zonation here. But this is hydrothermal zircon growing in a really weird environment. So this has been looked at in some detail with some age debate that our data, I think, informs a little bit. Here's, we're going to focus on this diagram for a little bit. So the top is 1,600 million years ago, 1.6 billion years ago, bottom 2.3 billion years ago. So we're going way back in time, a huge swath of time that's represented with some pretty dramatic, here's this diabase dike swarm, intrusive suite, shear zone development and reworking throughout this time period here, and some early geochronology. We'll focus on the oldest stuff here is the granites surrounding it. So some of the early work, Sam Bowering and others, documented what they thought, this is zircon data. So this is zircon isotope dilution thermal ionization mass spectrometry data. So really precise data. They're dissolving individual zircon grains here. And they had two of these Discordia arrays, two different linear arrays, A and B. A is 2175, it's that data point right there. B is 2090, and it's that one right there. And they argued that this is the granite complex, and this is hydrothermal alteration. And that was their initial argument. Some later work came in and documented, yeah, we see this. We see this Gray Slate granite. We see the Nechalacho layered suite. It's all 2.175. So all the magmatism, if I go back to the map, all the magmatism here, here, here is all 1.75. They did not see any evidence for a 2.1 billion year old event at all. Instead, they saw monazite at 1.85 billion years. So they argued that this was an artifact to this 2.1 billion year old age, and there was no alteration or overprinting at that time. So a recent paper just came out from the Alberta group, looked at actually the ore minerals. So they dated bastnasite, which is a rarothermic carbonate mineral, and they dated it with uranium lead and looked at some neodymium isotope compositions. And they came up with two ages. The bulk of the data, the bulk of the bastnasite has a 1.8 billion year old age, and this is associated with reworking of some of these major faults in the area. And then they also have hints of an older age, a 2.05 billion year old age. So somewhere in this 2.1 ballpark here as well for bastnasite. So things are moving around. It's a fluid-rich environment over hundreds of millions of years of overprinting and resetting. So again, Eric and Renan were heavily involved in this. Niles took the first crack at it in his thesis, and then Andrew has followed up this year for his thesis project. Here's one of these complicated zircon agglomerates, basically. These are a bunch of little tiny zircon crystals that form this monster. So this is a huge aggregate grain. This is a microprobe map. So this is just zirconium concentration showing it's all zircon, high zirconium. What Niles did is he put these laser ablation spots. So he just did a transect across to see if there's any kind of weird zonation that we could see in just a cross section there. So we did the laser ablation data. There's all the spots on our Concordia diagram, the uranium lead geochronology spots. And then here's just a histogram and a kernel density estimator of that data. And you can see it's kind of centered on 2.1. We don't have huge evidence for a peak 2.175, which is the magmatic age, and no 1.8 overprint either. So we were thinking, oh, maybe the hydrothermal age is 2.1. We looked in closer, looked in more detail, and with the new SEM, Andrew has been working with Mo to get these beautiful images of these little zircon grains. So each one of these is a little zircon fragment, and these are not normal zircon shapes. These are clearly hydrothermal. Each of these circles is a 30 micron laser ablation spot. And you can see that there's nice clean rims and some kind of rotten cores in here. So if we look at this grain right here, we see the rotten core and a nice rim, or relatively nice rim. And the core has that sort of speckled color, that vacuolized, rotten out color with some bright stuff in there, might be uraninite. The rim has a relatively clean look to it, which usually means that's a pretty nice mineral grain. It should give us decent ages. And it's actually cracked. So you can see these cracks in it. And this is pretty common in zircon, in the zircon world, where you have, in many instances, you'll have a high uranium core of a zircon grain with a lower uranium rim. And as uranium decays to lead, it kind of blasts apart the crystal structure, and zircon doesn't self-anneal. So it remains in this metamixed state. And if fluids infiltrate, they can actually expand that zircon lattice, and that expansion can crack the pristine zircon around it. So these are kind of expansion cracks of the surrounding zircon. The classic interpretation of these cracks would be. So this looks all the world like a normal zircon, old core. The rim is younger because it grew around it, and then its expansion cracked at a later date as this thing accumulated radiation damage, and maybe this one didn't. We went in and did some mapping here. So this is a hafnium map. Again, we'll see that this is one, I can't really see it, but that's 1 weight percent. So that's a normal, not a crazy amount of hafnium. It's high, but it's not crazy. We have this hafnium zonation in the rim from low to high. Phosphorus, pretty high phosphorus content in here for zircon. The core is kind of normal. The rim has this zonation to it. Still trying to work out what the zonation might mean. And there's fluorine as well. Small amount of fluorine, very small, maybe not quantitative necessarily, but looks like there is some fluorine in the rim and there's not in the core. So we're seeing this fluorinated zircon again in the rims. If we look at the rare earth elements, so all these spots, we get ages with the laser and we get the trace element concentration of the zircon grains. And so we went through to these ones. Let me go back to this image, and we characterized them as sort of a really nice clean rims, cores, these kind of dirty rims, or something in between. And these are the rare earth element profiles of these hydrothermal zircons. And these are crazy hydrothermal zircon compositions. These are ridiculous. Normal zircon would look a pattern something like this, maybe like this, if I could draw that out. And so these are not normal igneous zircon. These are growing from something different, or they're replacement. So these could be replacing any number of maybe eudialyte, a zirconium rare earth element mineral, in inheriting the rare earth element pattern in some way. But the cores and rims, if I zoom in on the cores and the clean rims, they're broadly similar. The cores have more heavy rare earth elements and less middle rare earth elements, but they're not too different from one another. It's when we get to the ages where it gets kind of curious. The rims are older. The rims are this darker orange, are older than the cores. And this is confusing. The rims are clearly not older than cores because they're rims, so they can't be older. So what's going on here? Well, the rims, I mean, we have one rim. We need more data to really answer this question, but I've plotted on here the igneous crystallization age, 2.175, for the granitic complex, or the igneous complex around it. This possible resetting age from some zircon and definitely some from bastnäsite, and then the metamorphic monazite age. And so it's possible that the rims, the cores must be older than the rims, but the rims are recording this definitively older age. So which means that the cores must be reset and the rims not reset, which is kind of interesting. You could debate when the cores have been reset, and I'm not sure about that. But when we, just to show some more of the kind of depth of data that we get, if we zoom in on these 3 spots that we put on this one zircon grain, rim, core, rim, we can plot our data. When we drill down with the laser, we can separate out the depth intervals. Each depth interval that we drill down into, we can get a data point out of. It ends up being very imprecise data, but we get a time series through it. So we can kind of get a window into what the 3rd dimension looks like here. And so these are color coded, where the core is this yellow and the rim, both rim analyses are there. And so the rims are enriched in aluminum. This is not a real concentration. It's just a relative concentration, but the rims are enriched in aluminum. They're loaded with aluminum. That's not normal zircon. The cores have more normal, like altered zircon aluminum concentrations, but record this younger age. If we just plot kernel density estimators for those data sets, the rims are kind of getting up towards the igneous crystallization age, but in this resetting zone here, and then the cores are certainly younger. So I'm not entirely sure what to make of this data yet. We need to get some more information on it and collect some more data, but I think it's entirely possible that the cores are older, the rims are younger. They both crystallize pre or close to the igneous crystallization event. So this is like hydrothermal activity running amok in this system soon after igneous crystallization and growing this hydrothermal zircon. And then maybe during this metamorphic event, the cores got altered and lost lead and kind of got pulled down towards Concordia. So they were up here and they got pulled down towards this event at a later time. But the rims were somehow immune to that lead loss event. So maybe there's some sort of preconditioning going on to the zircon that is allowing it to either be more susceptible to alteration, or in the case of the rims, less susceptible to alteration. And this is an ore mineral actually in these deposits. So there is a lot of zircon on here. So it's not a non-trivial question of what stabilizes zircon in these systems. How do you get it out? How do you get the metals out that we want to? I think it's a really important question, and looking at some of these hydrothermal zircons could give us some insights into that. And one idea, so maybe these cores are inheriting old lead. I think that's not likely, that the rims are getting pulled up artificially. I don't think that's particularly likely. I think it's more likely that there might be preferential alteration of the core, and that maybe this fluorine or some other element that we have yet to sort of think about helps stabilize the rim zircons here and prevent them from being altered later on. And fluorine is a really interesting one, and I'm curious about this fluorinated zircon we're seeing in multiple locations, because fluorine is well known to stabilize biotite and phlogopite to higher temperatures. So it stabilizes the mineral to higher temperatures and prevents melting. But then when it does melt, when you do melt out biotite, release a lot of fluorine into the melt. And so this high temperature melting, Andy Smye had a recent Nature Geoscience paper talking about high temperature melting and the stabilization of continents, and how fluorine interacts in this system will probably be pretty important to work out. So here are some sort of ending thoughts. I wouldn't dare say conclusions. I'm happy to hear any thoughts or concerns or ideas you have on any of this data, because we're new in this space and thinking about it and collecting a lot of data. And I'll just end by saying thanks to Roland and Deborah Sauerman, who endowed this Slingerland Early Career Professorship named after Rudy, which I've had for the last 3 years and used to. Without this money, I would not have been able to get into the critical minerals space. And so all this work that I've shown has been funded by that. So with that, happy to take any questions. Thank you.
I'm curious about Mount Mica.
Yeah.
And in particular, that young age.
Me too.
So
do you have any ideas?
I do.
Okay,
but
good.
I'm wondering, I didn't catch the error bars on the date.
The lower intercept's like 20 million, 18 maybe.
So
and you know, that's I wouldn't die by that uncertainty. That could move around
so
a bit
it
with
could
more
be
data.
100.
We'd have to get more data that pulls that up before I would say 100 probably. I think it could be.
Well, so here's my thought.
Yeah.
Not too far away in New Hampshire, the Ossipee and
Yeah.
Belknap ring dike.
Yeah.
You know, they've got dates pretty close to 100. And if you follow the track.
So we are over here then, right?
Up into Vermont, you know, by the time you get into Vermont, there's
the hotspot track.
The hotspot.
Yeah.
So you might be able to get yourself a 90 or 100.
Okay. Coming out there. Yeah.
I'm just making that.
Yeah, that's I think that's the peak in the compilation here from Dwight. Oops, I'm going the wrong direction. From Dwight is that peak is the I'm going the wrong way. I'm sorry. Getting very confused. There it is. This stuff here, right, is the hotspot track. The tail of this is the hotspot. I think. Double check that, but yeah.
While we're on Mount Mica, have you looked at boron in the zircons?
No, I've not.
On this, if you were trying to follow up on this opening of myelolytic cavities, if they are producing a fluid that is generating tourmaline on the edges of the garnets, that would have to be a very boron-rich fluid that is doing that. And you might be able to see that in the zircon.
Yeah. Could we get it with a microprobe?
We can. I mean,
Yeah.
depends on how much.
Okay.
Depends on how much is there.
Yeah, of course. Well, even, I mean,
Also, you could do it with a laser, and I'm wondering, maybe you already did.
ooh, well, I don't,
No more.
I don't
Okay.
think we've put that, Eric could
Okay.
probably weigh in better. We have to check. I don't think so. If it did, it was like throw it in for, and we never look at it. But that's a really good thought. I mean, even with the microprobe, I'd be more inclined to kind of trust the microprobe on this, because even if we just had things like fluorine, where we're not quantitative at any one pixel, but we get a general sense of, is there more fluorine relatively in the rim than the core would probably be, or boron, excuse me, in the rim relative to the core would be interesting.
Yeah.
That'd be interesting to look at.
I almost want to say that boron and fluorine can be friends.
Yeah.
Also,
Yeah.
I think.
Well, there's a weird literature on the substitution mechanisms of fluorine in here, and weird stuff like F4 going in for like the silicon tetrahedron, and some zircons, like some of these hydrothermal things, it seems like there's a one-to-one relationship between silica depletion and fluorine enrichment in these zircon grains. So the mineralogical substitution mechanisms confound
Yeah,
me.
it's like
So-
you're running some HF through there.
Yeah, exactly.
Coming off the silicon.
Exactly.
Making fluorides.
That's a good idea to test the
So
mirror cavity thing.
that might be something worth looking at. And then do you know, I couldn't remember which ones had phosphorus in the rims. And which ones
These
didn't.
ones, Mike, do you remember if there's a lot of phosphorus? I didn't show it, but do you remember the magnitude of the phosphorus? don't know if
Ooh, at any rate, if you have phosphorus also, if you've got a lot of calcium in the rims, a lot of phosphorus in the rims, fluorine, rare earths, you might want to look at what's happening with apatite in the system overall. If you've got some kind of distribution or like
Yeah.
an apatite line somewhere
Sure,
that
sure.
might.
So the origin of these samples these came from Dwight, and he was doing, when he sampled these in like 2014 or 2015, his claimed that he was grabbing them from the pit. These, in this particular sample, he thinks it's from near the Garnet line, but isn't quite sure. It's kind of from the waste pile rocks. So, concerted sampling across these lines and across the pegmatite would be a really interesting, a really useful thing to have that sort of outcrop scale spatial resolution across these zones. So, yeah. Cool. Thanks.
Other questions?
So this is a question from a geophysicist who doesn't understand much of what you said, but how do you alter the core without altering the rim?
It's
Is it because of the cracking, the fracturing?
Yeah, I mean, that's kind of we can do the exercise with that. Yeah, that's kind of the idea is, well, there's two things. When the zircon itself becomes metamict, so, there's these cool videos that are sort of schematic representations of what happens when decay occurs. So you got a uranium atom sitting locked in the lattice, and it's like a shotgun. The alpha particle goes out one direction, and the recoil is the thing that does the damage. So the uranium atom decays, it recoils back and blasts a hole into the lattice. And if you do that enough times with a bunch of uranium, and it's not just one, for uranium to get to lead, it has to do that a bunch of times to get down to lead. And so if you do that enough times, you create a metamict zircon where the domain is, there's a lattice of good zircon, but it has, basically there's percolation points to it. So fluids can percolate into this damaged grain and get in there. That's a pretty difficult process, because that's like that's a reactive flow kind of thing. So it can fluids coming in can kind of self-anneal and prevent further percolation. So these cracks are probably the way that you might get stuff in through that nice rim. But this rim is clearly not normal zircon. And so it could be a pretty distorted lattice as well. That's also radiation damaged. That's a question for maybe Peter can answer some of these things, like what happens at the crystal structure scale. I was still thinking about that. That's a good question. I don't know how to explain I don't have a great explanation for this, this younger age from the cores compared to the rims. But I have an inkling that it could be important for, the zirconium and rare earth element distribution and how it's moved around in these rocks, because this is an ore mineral at these grades. So, yeah.
Any other questions?
So Jesse, going back to the Mount Mica, I was wondering if you could elaborate a little bit. I think I lost the thread of. So I see that there are these cavities, right? which look like sort of fluid release features to me.
Yeah. Oh,
Wow.
the schematic.
Yeah, or like, yeah, so these
Here?
ones, right? So
Yeah.
you have these cavities, and these look sort of to me like sort of two-phase flow, sort of flow features. You're forming some instability. But then, if I understood correctly, we're suggesting that one option could be that these were closed for sort of 100 million years and then burst. Is that right? Versus like having using
I
them
don't know if
as
I'd say
fluid.
proposal, but a loose hypothesis-ish thought. Yeah. Something. I mean, yes. Either that, or I mean, that's arguing that this is ultimately internally derived fluid that's creating these rims. I'm cautiously cautiously convinced that this age regression has some meaning, that lower intercept age has geological meaning. Whether that's a like muralitic cavity rupturing at 70 million years, like you said, 180 million years after the pegmatite formed, or whether it's another fluid coming through that's rich in fluorine and calcium and all these goodies. I don't know. I'm utilizing that sort of master's thesis idea of the cavities being associated with lithium mineralization being associated with the garnet alteration. So making that connection between the zircons, and that would be an important thing to address that. So I'm sorry, I didn't get your question, I don't think,
No,
but
like I just want to clarify, because I think to me, sort of conceptually, like having these at high permeability pathways makes sense, right?
Yeah.
So if there's subsequent fluid coming in, it could use it. For it to sit around whatever 150 million years when there's tons of tectonic activity around, and those fluid just like not diffusing
yeah.
out into a messed up
That's a
lattice
totally fair point.
seems a little bit unlikely to me. But
I think that's a totally fair point, and I think there's I think hints in the pegmatite geochronology literature that the high concentration, the really juicy ore deposit ones have multiple phases of stuff going on, and whether that's sort of internal re-enrichment processes, or whether it's like multiple externally derived enriched fluids coming in, I think is an open question. But that's a totally fair point about the cavity sitting there as a cavity for 150 million years.
All right, that's good. Are there questions online, or it's
Dave Rust is asking, are you also working on carbonatic pegmatites?
No, not currently. These are the two pegmatitic projects we've got going on at the moment. So no, we've got other weird zircon stuff that Renan's doing her PhD on that is associated with more with copper porphyry formation, which is in a different category of crazy zircon compositions, but not carbonatitic ones.
I want to follow up on Andy's question, being a sedimentary geologist.
Yeah.
Well, so I'm curious. Early in your talk, you said these things are igneous,
Zircon.
pegmatites,
Pegmatite.
igneous-ish.
Igneous-ish.
And now, and I'm listening to this, internally derived fluids, and like,
yeah.
where does it become metamorphic, igneous?
Oh God, how we need a couple beers to talk about this one. Wow, it's a great question. So igneous, the traditional definition of igneous would be like a magma. Experimentally, we think it solidifies at 680 degrees centigrade. And so that's the solidus. And so anything above that is igneous, less than that's metamorphic. But we can move a lot of elements can move in fluids. Metamorphic stuff moves around, like we know this. So I think it's an open question. And the pegmatite literature has kind of been bifurcated into pegmatites being associated with ore bodies. So ultimately it's fluid derived from the ore body, from the granite, and it's exolved off the granite into the surrounding country rock. And so the lithium enrichment, the cesium enrichment, the tantalum enrichment is brought in by the magma, and then that's deposited into the sediments itself. So that those initial plots I showed from the 95 work around South Dakota would be that kind of end member model. The other end member model is that it's partial melting or kind of sweat melting of the sediments. So the enrichment is sort of internally derived from the sediments, and then it's internally kind of being distilled into pegmatite bodies without really a magma associated with it. So those are kind of the two end members there, but they're both talking about high temperature fluids. You know, we're talking about 300, 500 degrees centigrade fluids that are aqueous fluids moving stuff around, moving a lot of stuff around in the crust here. And it's probably something, the answer is probably somewhere in the middle there. But it's kind of like, is ultimately are the critical elements sourced ultimately from the pluton, or are they sourced internally from the sediments? Is kind of the two end members, I think.
Seems to me that would be important to get a genetic model.
Yeah, exactly. Yes,
We'll have
exactly.
something to do for all the rest of you. Let's give him thanks
Thanks.
one last time.